We'll get right to it today. If you look, 7.2 is some radius chord relationships. So hopefully we have a working vocabulary now to understand what a radius is. That should have been pretty straightforward. Know what a chord is. RW is a chord. There's a quick little review here. The endpoints of a segment that lie on the circle. All right, and then they have some special relationships. So go through those, do a few problems, get you out of here in 15, 20 minutes, okay? It says the distance from the center of the circle to a chord is the measure of the perpendicular segment from the center to the chord. So what that's just saying is, if I ever ask you, or you're ever asked, what is the distance from the center of our circle, so from this dot here to the chord, that distance is always asked because if we look at it, we really can go some different ways to get to this, and these would all go to the chord, but all of these lengths are going to be a little bit different. So if you're ever asked what is the distance from the center to the chord, so that we know what that means, we have one defined value. The distance from the center here to our chord is always however long the perpendicular segment from the center to the chord would be. So I would want to go directly to this so that we would end up with a nice 90-degree angle here. And once I have a 90-degree angle here is whatever this value right here is, all right, that would be considered the length or the distance that the center is from your chord, okay? Second one, if a radius or part of a radius, so if we look at this one, here's A, here's D, that's our radius, is perpendicular to a chord. So here is our chord. And then it is clearly perpendicular because you are given this here, which tells us that we have a 90-degree angle, so they're perpendicular to each other. Then it would bisect the chord. So CB basically gets cut in half by the radius. Okay, so what that would mean is segment CE would have to have the same length, so be congruent to segment EB. So that means this here and this here, those have to be congruent to each other. Okay, so it cuts it in half. Third one, if a radius or part of a radius bisects a chord that is not the diameter, then it must be perpendicular to the chord. So it's kind of the opposite of this. It's basically just a different way of saying this. All right, they kind of are one and the same. It's kind of an if-then statement. If we know that our radius cuts this overall segment in half, which we would, because we're given this little mark here telling us that those two segments are congruent, then that would then have to mean that it is also perpendicular. So we would write that segment AE would have to be perpendicular to segment CB. Okay, so those two kind of are one and the same. And then last one, the perpendicular bisector of a chord passes through the center of a circle. So we would know that if we have, this is our chord, if we know we are both perpendicular and we're bisecting it, if we know we are both perpendicular and it's getting bisected, then the segment that is doing that, which is this guy, it would have to be going through the center of our circle. Okay, so then using those theorems, we'll go through a few of these problems, see if we can kind of keep all that straight. So for example number one here, it's telling you that AO is 5. So understand what AO is. This is your radius. DB is 2. So this segment right here is 2. So what they want us to then find, using those two measurements, find OC, OD, CD. OD is probably the easiest. I think it's the next one that you want to come up with. Well, maybe. There's a couple of easy ones. If I know that this is 5, then this whole segment here would have to be 5. So if we have 2 of it comprised from D to B, then OD here would have to be 3. So that then this whole length adds up to be the same length we have over here, which is 5. So OD, we know, must be a 3. The other one that should be pretty simple, if we know this is our radius, that our radius is 5, OC is also a radius. So if this radius is 5, this radius must also be 5, so OC is 5. The side that we are missing that we've got to do a little bit of work for is that side, the CD side. But if you remember Pythagorean theorem, we have a right triangle. So we know the Pythagorean theorem can be used. A squared plus B squared equals C squared. If here's our right angle, that means we know our hypotenuse is the 5. So that's our 5 squared. And then we'll let A be 3. And then we do our Pythagorean theorem. So 9 plus B squared is equal to 25. Subtract your 9 over, B squared would equal 16. Take our square root of both sides. We know we get a positive and a negative 4. But since we're talking about the length of a segment, there's no way we can get a negative answer for that. Sorry about that. So we know that the positive 4 would have to be the length of CD. Okay? So again, it's going to make you think a little bit. It's similar to what we had been doing before, where we got to kind of make some connections, make some jumps, and be able to put it all together to come up with our answer, which is good. It makes you think a little bit. Number 2, AB is 12. So we know this whole segment here is a length of 12. The radius of our circle is 10. So we can draw the radius in anywhere. So we could draw it here, we could draw it here, we could draw it here. It just doesn't do us any good because it's not really intersecting or dealing with the chord at all. So it doesn't really make us, or doesn't make a lot of sense to draw our radius in over here. So what we're going to do, so that we can use those theorems above, I'm going to draw in a radius of 10 through our chord, where we can now use all of those theorems from above, that this is a 90-degree angle. And then it also cuts the chord in half. So if this had been 12, what we would now be able to do, instead of putting this as a 12, we know that this length is 6. We know that that length would need to be 6, since the 12 got cut in half. All right. We would also know that that full length is 10. The radius would be a 10. So what I'm now going to do with a radius, I'm going to draw in another radius, and the radius I'm going to draw in is going to go from O to B, because this also goes from the center of our circle out to the circle itself. We know this is 10. And since the question is asking how far is the chord from the center, that would be this length right here. So if we now kind of think of this as our right triangle, from here to here to here, we know 2 of the 3 sides. So similar to what we did in the last one, set up a little Pythagorean theorem problem. A squared plus B squared equals C squared. We know C is 10. That's our hypotenuse for that red triangle. And then we would do x squared plus 6 squared. So this side, this side, this side, we're using the Pythagorean theorem. X squared plus 36 is 100. Subtract the 36 down to the other, or over to the other side. X squared would be 64. Take our square root. We get positive and negative 8, but we know it has to be a positive 8. So it is 8. X must be 8. That's how far the center is to our chord. Okay? 3, the chord is 15 units from the center of the circle. So when a chord is said to be from the center of our circle, that's giving us this length right here. We have a radius of 17. So again, it doesn't really do us any good to draw in a radius here or here or here. So we wouldn't want to do that. We want to somehow be able to draw it in so we can intersect, deal with our chord. You can see we're dealing with some Pythagorean theorem problems here. So the radius that I am going to draw in, get back the pen, the radius I am going to draw in is going to go from the center of our circle out to B, and then I would know that this is 17. So if we then kind of look at what we have here, the question is asking you for the overall length of this chord. But what we can now do if we think about this triangle here, from here to here to here, what we can then figure out is that length using the Pythagorean theorem. So that's what we're going to do, figure out this length right here. So we have, I'll do it over here, x squared plus 15 squared equals 17 squared. Do our Pythagorean theorem, figure out what those are. So x squared plus 225 would equal 289. Subtract your 225 over, you'll get 64. Take our square root of both sides. X would be 8. Now, a little tricky here, just in the sense if I come get rid of this x, we now know, I don't know why it keeps doing that, we now know that this length right here is 8. The question was looking for the length of the entire chord, however. So 8 is from here to here. This length here then, since this would be cutting that chord in half, this would have also have been 8. So the length of our chord must have been 16. All right, the 8 and the 8 added together. All right, last page. These two, a little trickier. I need to think about these a little bit. So let's kind of sketch in what we have here. You have a radius from the center of our circle is 13 meters, and then the length of the chord of a chord, PQ, is 10. So let's draw in a chord. Wouldn't matter where you drew this in. So let's draw our chord in. Call this P, call this Q, and then we know the length of this is 10. The radius of the circle is 13 millimeters. We want to figure out what is the distance from O to PQ. So O is the center of our circle, and then directly to PQ means we want to find this distance right here. The length when our chord and the radius or the segment drawn from the center is perpendicular to our segment. When that happens, what that does is it now takes this 10, and we would know that this would have to be 5, and that would have to be 5. Okay, so that's what we can conclude from this. Then if I draw my radius in, we could have extended it here. And when I first kind of went through this, just kind of refreshing my memory on all of this and how we can do each problem, that just doesn't really do us much good. So I'm going to draw in a radius of 13 to Q. Okay. Once we have that, if we're looking for the distance from O to PQ, that means we're looking for this distance right here. And then yet again, just a simple little Pythagorean theorem problem that we work our way through. So a squared plus b squared equals c squared. For us, that's x squared plus 5 squared equals 13 squared. All right, so 25, 169, subtract that over. We would get 144. Take our square root, and then x would equal 12. All right, and then that's our distance from the center of our circle to the chord. All right, last one. Again, a little trickier. These last two, a little trickier. This one in particular, 2 circles intersect and have a common chord of 24 centimeters long. So you can see our 2 circles are intersecting. The only place they could possibly have a common chord would be from here to here. So if we connect those to create our segment, we would know that this has to have a length of, not 12 that I wrote down, it would have to be a length of 24. All right, the centers are 21 centimeters apart. So if I put dot here, the centers, do my best to connect these. We know that this is 21. So right now, I'm going to draw it in over here so it doesn't get too messy. We know that length is 21 centimeters. Then it says the radius of one of the circles is 13 centimeters. And then we want to find the other radius. Okay, so a couple things. When we draw in a chord, so this was our chord here, and then we draw a radius through this chord, all right, then we know that this is going to be a 90-degree angle. All right. What that also then tells us is that that 24 for the length of the chord gets cut in half. So instead of 24, get rid of this. Oops. Let's see if I can get rid of this guy. Yep. Instead of the 24, we're now going to write this one as, come on, 12, and this one as 12. Make that a little more clear. Get out of here. There we go. All right, then it says the radius of one of the circles is 13 centimeters. Okay, so what I'm going to do is draw in a radius to one of the circles. I am going to use this one. And I would know that this must be 13. Similar to the last couple, we'll need to kind of make, some connections and such after we do this. But we have a right triangle now. So if we look from here to here to here, we have a right triangle. We can figure out what that length is right there. So we'll do x squared plus 12 squared equals 13 squared. All right. So x squared plus 144 equals 169. X squared would equal 25. Take your square root. X would be a 5. So what that now tells us is, instead of the x, we will put a 5 right there, if I do this correctly. So we know that this segment is 5. So if you then come back to what we had written here, the entire segment, so so this entire segment was 21. So if we have 5 of it comprised right here, then we would know that from here to the chord, this would have to be 16. All right. So hopefully that makes some sense. Now, it still doesn't answer our question, because what we are ultimately looking for is, what is the radius of the other circle? So we are looking for, what is this length right here? So now I'm going to call that y. That's ultimately the answer to our question. But now through our work, let's look at a new right triangle. Let me try to do this in a different color. Let's see how blue works. If we now look at this triangle here, here, and here, we have a new right triangle that we can still use the Pythagorean theorem for, and then y would be what we're trying to find. So we set that up. We'll do that to the left. Y is your hypotenuse. Here is our 90-degree angle, so now y is a hypotenuse, so we'd have to do 12 squared plus 16 squared equals y squared. I know 12 squared, 166, let me just make sure, or 16 squared, let me make sure. Yeah, 256. Oops. Is equal to our y squared. So y squared is equal to 400. Yeah. Take our square root, and it should work out nicely to be 20. So then we know this radius here had to have been 20. All right. So there's a little bit more of circles. Not too bad. Just, the big idea is that when we find the distance from a radius to a chord, it's always form through a 90-degree angle directly to the chord, and then it cuts that chord in half. Everything is kind of based off of that, and then you can remember some Pythagorean theorems to get you through. So I'll leave you a little assignment to go with this. It's pretty similar, and hopefully we're good to go. So hope everybody had a good week. Be safe, stay healthy, and we will see you next week.